right, guys, here's your 8th grade benchmark review. Remember, we're going to be having our benchmark the Tuesday we come back from spring break. That's March 19th. So we are to classify these as potential or kinetic energy. So here I've got stored energy, gravitational energy here that kind of tells me that has to do with how high something is. When you lift an object off the ground, again, has to do with height. So, or elastic energy when you stretch a rubber band. So all of that is stored energy. That is considered potential energy. And the next one, the energy of motion. Anytime you have motion, that is a kinetic energy, and you need to know that the faster an object is moving, the more kinetic energy it has. So that is kinetic energy. So looking at this graph here, what two places on the graph is potential energy the greatest? As I said, potential energy has to do with height. It also has to do with mass, but in this case, we don't know anything about the mass, so we're dealing with height. So the higher it is, the more potential it has. I like to think of it as the higher I am, the potential for me to injure myself becomes greater and greater. So the highest point on here is going to be A. Kinetic energy is the greatest when it is moving the fastest. So as we know, as we go down, those of you who have ever ridden a bike down a hill, the faster you go fastest, the further you go down the hill. So the fastest is going to be right here at the bottom. So that is going to be D.
Okay, next section is the speed, distance versus time graph. First question, how many total miles did this car travel? Well, miles is over here on our y-axis. The total miles, it traveled from point A, all the way up to point E. And at point E, it had gone a total of, we're right there. If we look at the amount of lines between each number, these are going by tens. It's 10, 20, 30, 40, 50. So if this is 200 right here, then this must be 210, which means the total miles is 210 miles that the object car traveled. Now, letter B, what was the average speed of the car at point E? Well, speed is equal to distance over time. And it's important since it says at point E, the average speed is total distance over total time. So at E, the total distance traveled, we already figured that out, was 210 miles, divided by the total time. Well, at E, it had gone a total of 25 hours. So 210 miles divided by 25 hours is going to be equal to 8.4 miles per hour. It's a slow car. It's a very slow car. Describe the motion of the car between 5 and 10 hours. All right, here is 5 hours, here is 10 hours. At the beginning of the 5-hour mark, the car had traveled 60 miles, and at the end of that time period, the car was still at 60 miles. So did the car go anywhere? The car did not, which means it was a couch potato car, and it was at rest. D, describe the motion of the car between D and E. At D, we've got the car having traveled 20 miles, it looks like. And of course, at E, it had traveled 210, or the rest of the trip of the 210. On a distance time graph, when we see a straight line, that it's not a flat line, a straight line, we know that equals constant speed, which means the object was not changing its speed or direction. It was going a constant speed and a constant direction. Okay, use the formulas for speed to calculate the following distance and time measurements. Speed is distance divided by time, so speed equals distance, that's it, divided sign, divided by time. Number 2, a car travels 300 kilometers at 3.5 hours. What's the average speed? Very simple. We take 300 kilometers divided by 3.5 hours, put it in our handy calculator that we all get to use this year, and our answer is 85. And it's 714. Since that 4 is less than 5, we're going to leave the 1 as it is. And our answer is going to be 85.71 kilometers per hour. And number 3, a cheetah runs 3,600 miles in 6 hours. What is the average speed? Again, we're going to take 3,600 miles divided by 6 hours. The cheetah's average speed is 600 miles per hour.
It's a very fast cheetah. Okay, so here we're doing Newton's laws. We need to look at the image and figure out which law does it best describe. So we have two different shopping carts here. This tells me we have two different mass. This is going to be a very low mass right here, and this is going to be much heavier. So we're going to just put light here, heavy here. Anytime we are dealing with two different masses, I know that is the second law. So that's how I remember it, is two masses, second law. So that is force equals mass times acceleration. So that tells me that I'm going to, if I have a small mass, let's say of 2, and I apply a force of, let's say, 5, then my acceleration is going to be, that doesn't go. If I have mass force of 10, then my acceleration is going to be 5, because 5 times 2 is 10. If I have a large mass, like let's say 10, and I apply the same force of 10, then I am going to have a much slower acceleration of 1. So this is going to be much slower, which makes sense because this is my heavy object right here. And this one is going to be a lot faster acceleration. And we all know that fast things, lighter things accelerate a lot faster. All right, next one, swimming. Swimming. So the motion of swimming is that you push forward and you push backwards up with the water and you move forward. So that is going to be my third law, which is for every action, you have an equal and opposite reaction. So you push forward to move backwards. You push backwards to move forwards, excuse me. All right, and then last one, the golf ball on the tee. This is going to be Newton's first law, which states that that an object at rest will stay at rest, or an object in motion will stay in motion in the same speed and direction until an unbalanced force acts upon it. This is at rest, and it's going to stay there forever and ever until that ball will stay until a club or another unbalanced force hits it. Remember, this is also known as the law of inertia. All right, here we're calculating the net force. So we know that if they are traveling in the same direction, we add them together, or if we are traveling in opposite directions, we subtract them together. These are traveling in opposite directions. I'm just going to kind of make these a little bit bigger arrows. These are working against each other, so 4 minus 2 has a net force. 4 minus 2 has a net force of 2 newtons. That would be considered unbalanced because it is moving. We cannot assume it's moving at a constant speed, so the direction the object moves is going to be left, and it is considered unbalanced. B. Same thing here, we've got these traveling in the same direction. So that's like you're pushing and another friend decides to get on the other side and pull. So if you're working in the same direction, then we add those together. And that is going to be a net force of 6 newtons. Again, it is moving, so that it's considered unbalanced. Again, we cannot assume it is traveling at a constant speed unless it tells us it's traveling at a constant speed. So the direction the object moves here is going to be right, and I apologize, I had this is also right, because 4 is bigger than 2, so both of these are going to be moving to the right. Identify the following examples as balanced and unbalanced. So what we know about balanced is that it is either at rest or moving at a constant speed. Okay, it would be balanced. If it is considered unbalanced, that means it causes a change in motion. So whether a change in motion can be a change in speed or direction. So a car traveling at a constant speed, okay, of 60 miles per hour, that has to do with, there's my balance right there. As long as it's traveling at a constant speed, it's not causing a change in motion, so it is considered balanced. A person riding an elevator up and down. So in order to ride an elevator up and down, you need to move, you need to stop, and then you need to change direction. So you're not only changing your speed, but you're also changing your direction. So this is a change of speed and direction. So this one is considered unbalanced. A ball at rest in the field. So if it is at rest, it is considered not changing its motion, so it is considered balanced.
All right, we're going to calculate some force. This is Newton's second law. Formula is right here. Force equals mass times acceleration. We taught you guys to use this triangle. We draw our little dividers there, and the F would go on top because the formula states that F equals ma. So the times is right there. Those two would be divide. Remember, we're going to cover up the one that is missing that will give us the formula. On this first one, we have 150 newtons of force and 6 kilograms of mass. So we are looking for the acceleration. If we cover up the acceleration, the mouse is clicking over there, then our formula would be force divided by mass. So our formula would be force divided by mass. So we come over here, the force is 150 newtons. We're going to divide that by the mass of 6 kilograms, giving us an acceleration of 25 meters per second squared. Meters per second squared is the unit for acceleration. All right, on the second problem, we're missing our force. There's our unknown. We have mass of 12 kilograms and 18 meters per second squared. So we come over here, we're going to cover up the force, leaving us with m times a. So it would be force equals mass times acceleration. The mass is 12 kilograms. Our acceleration, sorry, that's a times, is 18 meters per second squared, giving us a force of 216 newtons. 216 newtons. Next problem, we're missing our mass. So we're going to come over here. We're going to cover up the mass, leaving with this F divided by A. So mass equals F divided by A. Our force over here is 744 newtons divided by an acceleration of 24 meters per second squared, leaving us with a mass of 31 kilograms. And the next problem, we have 480 newtons, 15 kilograms. Our unknown, of course, is acceleration. So we cover up acceleration, leaving us with a formula of F divided by AM. Our force is 480 newtons. 480 newtons divided by a mass of 15 kilograms, leaving us with an acceleration of 32 meters per second squared. And finally, we have no force. We are given the mass and the acceleration. Without force, the formula is force equals mass times acceleration. Our mass is 73 kilograms times 93 meters per second squared, giving us a force of 6,780